Hello students, welcome back to my YouTube channel Chemical Funda. In today's video, we are going to learn about quantum mechanical model of atom. Classical mechanics studies with motion of all macroscopic objects like falling stone or orbiting planets. So all these object studies was done in classical mechanics. But such particles, those are having particle-like behavior, we have already studied in our previous section. Now, what about microscopic objects like electrons, atoms, molecules? So for that, a new branch of science that deals with the study of such a microscopic objects, and that branch we called as a quantum mechanics. So the branch of science that takes into account this dual behavior of matter. So what is this dual behavior? Matter's dual behavior like particle nature and wave nature. Particle-like properties and wave-like properties, this dual behavior is studied in the branch that is called as quantum mechanics. So this quantum mechanics studies the motion of the microscopic objects, whereas classical mechanics it studies the motion of all macroscopic objects. When quantum mechanics is applied to macroscopic objects, it gives us the results same as those from the classical mechanics. So this quantum mechanics when applied to macroscopic object, actually they are studies with the microscopic object, but when they applied to macroscopic object, they are giving the same result as those of from the classical mechanics. This quantum mechanics basically developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. Werner Heisenberg and Erwin Schrödinger, these two scientists developed this quantum mechanics. The fundamental equation of quantum mechanics was developed by Schrödinger, and this equation can be called as backbone of the quantum mechanics, and it won him the Nobel Prize in Physics in 1933. So for this Schrödinger equation, he won the Nobel Prize in Physics in 1933 to Erwin Schrödinger. For a system such as an atom or a molecule whose energy does not change with the time, the Schrödinger equation is written as h cap psi is equal to E psi, where h cap is a mathematical operator and it is called as Hamiltonian. So this equation is written for an atom or molecule whose energy doesn't change with time. H cap psi is equal to E psi, where H cap is a mathematical operator and it is called as Hamiltonian. Now we will see hydrogen atom and the Schrödinger equation for the same. So when this Schrödinger equation is solved for the hydrogen atom, it comes out with the possible energy levels that the electron can occupy and the corresponding wave function psi of the electron associated with each energy level. Okay, so when this Schrödinger equation is solved for the hydrogen atom, that is the element containing one electron, it comes out with the possible energy levels that electron can occupy and corresponding wave function, that is psi of the electron associated with each energy level. So these quantized energy states and corresponding wave functions are characterized by the set of 3 quantum numbers. So this quantized energy state for the hydrogen atom and its corresponding wave functions, they are characterized by 3 quantum numbers, namely principal quantum number n, azimuthal quantum number L, and magnetic quantum number ml. And all these 3 quantum numbers we are going to discuss in our next video. They are very important part of this lesson and we will see them in a next video. So these quantum numbers arise as a natural consequence in the solution of the Schrödinger equation. The wave function, actually it is a mathematical function whose value depends upon the coordinates of the electron in the atom and that does not carry any physical meaning. So they are simply coordinates of the electron in the atom and they are not having any physical meaning. So the wave functions of a hydrogen or hydrogen-like species with 1 electron are called atomic orbitals. So these wave functions for the hydrogen or the species which contains 1 electron are called as atomic orbitals. And this wave function pertaining to 1 electron species are called one-electron system. So these wave functions, those contain 1 electron, are called as one-electron systems. And the probability of finding an electron at a point within an atom is proportional to the psi square at that point. So in an atom, probability of finding electron is proportional to psi square and it is a function. It is a mathematical function. Due to increased nuclear charge, all the orbitals are somewhat contracted. In multi-electron species, if you will see, its nuclear charge will increase and due to that increased nuclear charge, these orbitals are somewhat contracted and therefore this Schrödinger equation, it cannot be solved exactly for a multi-electron atom. Just now we have seen due to increased nuclear charge, all the orbitals are somewhat contracted. So this Schrödinger equation cannot be solved exactly for a multi-electron atom because the energies of the orbitals in multi-electron atoms depend on the quantum numbers n and l. Therefore, this equation cannot be solved exactly for the multi-electron atoms. Now we will see some important features of the quantum mechanical model of atom. So first important feature is the energy of electrons in atom is quantized. It means that it can have certain specific values. Quantized means it can take that only certain values and it cannot take any value in between those specific values. Second important feature is the existence of the quantized electronic energy levels in the direct result of the wave-like properties of electron. So the existence of quantized electronic energy levels are actually direct result of the wave-like properties of electrons and are allowed solutions for the Schrödinger wave equation. So these quantized energy levels are giving us the solutions of the Schrödinger wave equation and they are having wave-like properties of electrons. Both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. Already we have seen this concept in de Broglie hypothesis. The path of an electron in an atom therefore cannot be never determined or known accurately because its exact position and exact velocity is not determined. Therefore, we cannot determine the path of an electron it follows. Next feature is an atomic orbital is the wave function psi for an electron in an atom. So these atomic orbitals are the wave function, and that is psi, and they are simply mathematical functions and they are not having any physical meaning. And last feature is the probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function. Orbital wave function is here psi, so its square will be psi square, mod of psi square at that point, and here psi square is known as probability density and it is always positive. So this psi square will give us the probability of finding electron in an atom. So this is all about some important features of quantum mechanical model of atom. In next video we are going to see orbitals and quantum numbers. So stay tuned and watch this video and subscribe my channel, like this video, share it so that you will get notification for the next video. Thanks for watching. Thank you.